Good morning and welcome to this Conservation Applied Research and Development or CARD webinar, which will be reporting on Project Overcoat, an investigation of a novel panelized wall and roof system. Thanks so much for joining us today. I'd like to take a few minutes to cover some housekeeping items before we start. All attendees will be in listen-only mode. We will answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. The Q&A box can be opened by clicking the ellipse in the lower right corner of your screen as indicated on this slide. We'll do our best to answer all questions within the time allocated, but if for some reason we don't get to some questions, we'll answer them after the webinar. This webinar is being recorded and will be available on the department's website in a few weeks. The slide set from the webinar will also be available on the website, but if you need it sooner, email me directly and I can send it to you. Finally, if you would like closed captions on this webinar, click the CC bubble in the lower left of your screen. I am Mary Sue Lowenstein, and I'm the Research Planning Director at the Minnesota Department of Commerce, Division of Energy Resources. In that role, I identify and analyze gaps within utility conservation improvement programs and coordinate and plan research to fill the gaps. The CARD program is a major tool of that work. With me today is Laura Silver, a principal state program administrator at the Department of Commerce, where she reviews utility conservation improvement program triennial plans and annual status reports. Laura is the project manager on the research that is the subject of the webinar today and will be moderating the Q&A portion of today's presentation. Our presenters today are Garrett Mosman and Liz Kuschke from the University of Minnesota Center for Sustainable Building Research, or CSBR, and Connor Jansen from Slipstream. Garrett is a senior research fellow at CSBR. He holds an MS in architecture and is a lead accredited professional. Garrett's work at CSBR includes multiple projects exploring the application of exterior insulation systems in both new and retrofit applications. He also administers a program that equips commercial building operations staff to identify energy wasting malfunctions in their mechanical equipment. Garrett was the primary investigator on Project Overcoat. Liz is also a research fellow at CSBR, where she applies her passion for research-driven architecture and urban design. Liz has a Master's of Architecture and a Master's of Science in Architecture and Sustainable Design. Her work focuses on building energy use, learning from natural systems, and considerations of equity and social justice in the built environment. For Project Overcoat, Liz worked on construction details. As a technical service director at Slipstream, Connor provides consulting, design advice, and analysis to help clients achieve exceptional performance within the built environment in the areas of energy and indoor environmental quality and daylighting. Underpinning his technical background is a strong consideration of the challenges faced by architects and building engineers when working towards an integrated solution. On this research, Connor worked on marketplace analysis and estimated energy savings and carbon reduction for panel retrofits. Welcome to all of you. We look forward to the presentation. As always, I like to provide a little context. This webinar is one in an ongoing series designed to summarize results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. About $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. And results from CARD projects provide utilities with data to enhance energy efficiency program designs within their conservation improvement portfolios. As you can see by the pie chart here, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is the multifamily sector, and we'll report on an innovative approach which could offer a cost-effective way to upgrade roof and wall systems for increased energy efficiency. Now I'll turn it over to Garrett for today's presentation.
Thanks, Mary Sue. Here we go. Project Overcoat for low-rise multifamily buildings. A little bit, in the way of an agenda. We'll go through some background on the technology, and then we'll talk about the Overcoat Panel System and its details. And then Connor will come on looking at building candidates and building characteristics and modeled results and savings. And then we'll have some time at the end for questions and discussion. All right. Gotta keep up. I wanted to provide some background on where this came from. So on the left-hand side here is an image from a 2007 article in the ASHRAE Journal written by Joe Stiebrick of Building Science Corporation. The title of the article was The Perfect Wall. And what does that mean? Well, apparently we're having an Amber Alert. I guess that's what that means. Does it sound good? So the perfect wall consists of a sequence of layers, the first layer being the structure, the building structure, the exterior enclosure. Could be concrete block, could be wood frame construction, steel stud construction. And then over that are the control layers. So you have a layer that controls for air, water, and vapor movement. In our case, we use a peel and stick membrane for that, but other materials can serve. And then over that goes a thermal control layer. So this is rigid insulation, could be extruded or expanded polystyrene, could be polyisocyanurate or rigid mineral wool. And then over that goes cladding. And so that's the perfect wall concept as Joe described it. But this notion of this particular sort of sequence of layers has been around for 50-ish years and going under names like persist and remote. And then here at the University of Minnesota, we for years have called that approach EDAMS. So why would you do this? Why would you build a wall this way? One of the main benefits of the approach is moisture control. And I'm going to explore that. There's a lot of ways to look at that, but I'm going to look at it through the lens described in this great book by William Rose from the University of Illinois, Urbana-Champaign. The book's called Water in Buildings. And in it, he describes what he calls the fundamental rule of material wetness that says that cold materials tend to be wet and warm materials tend to be dry. So what does this have to do with the perfect wall? Well, we'll look at some wall sections here. This is kind of the key to the following sections and how they work. So here we have a wall section showing a stud frame cavity insulated wall. It's 70 degrees inside and 0 degrees outside. And then the red line shows the temperatures at various positions as you move from indoors to outdoors. No wall is thermally perfect. There's always some energy leakage. So there will be a difference between the interior wall surface temperature and the indoor air temperature. Likewise, there's going to be a difference between the sheathing or cladding temperature on the outside and the outdoor air temperature. So that difference on the inside between the air temperature and the wall surface temperature, if it's cold outside, like the example here, means that your body radiates heat to the wall and it's uncomfortable to be around, and it might feel like there's a draft. The difference on the outside, the warmer wall surface temperature compared to the outdoor air temperature, means that the wall is losing heat energy to the ambient condition, and so it's representing energy waste. So here's some variations on that theme. On the left there is showing an uninsulated stud wall like I have at my house. Now the temperature difference on the inside is much larger, which means that that wall is a lot less comfortable to be near. And similarly, the temperature difference between the cladding or the sheathing and the outdoor air is also much larger. So you waste a lot more energy with an uninsulated wall, which I think we would all expect to be the case. But notice here how the exterior sheathing and cladding materials are much warmer than in the second case, which is the one we looked at in the previous slide. So we're supplying that surface or those materials with heat from the indoors. And so we can expect them to be warmer and therefore drier, according to William Rose's premise. And indeed, it's true. These types of buildings, you can assault them with all sorts of moisture leaks, vapor diffusion, etc. And yet somehow they persist, and we don't see damage like we would if we began to add insulation. Now, on the right side is something like you're building a super insulated building, like a double stud wall, some type of construction like that, where you can get a really thick layer of insulation. So now we've almost eliminated the comfort penalty on the indoors because those surfaces are basically at indoor ambient air temperature conditions, and we've radically reduced the energy loss. But at the same time, we've made those materials that are outboard of the insulation much, much colder, which means that if there's a leak around a window or something like that, those materials are going to have a hard time drying out, and they're going to be a lot more susceptible to moisture problems. Now we'll look at the perfect wall. The perfect wall is shown on the left. There's no insulation in the cavity, and all the insulation is on the outside. So here you can see that all the structural materials are at about the same conditions as the indoor air. So we can expect that whole structural component to be dry because it's warm. The materials outboard of that become colder as they get closer and closer to the outside, but we don't care about that because these materials aren't moisture susceptible. Remember, it's foam plastic or it's mineral wool, something like that. So we don't care if there's moisture accumulation in those materials. Now, the second drawing shows what we call a hybrid approach. So there's some insulation in the cavity and there's some insulation on the outside. We can maintain the good moisture performance as long as we observe a proper ratio in R value between the R value that's outside and the R value that's in the cavity. And 2/3 of the R outside and 1/3 of the R inside is definitely safe. And in this climate, we can go to 50-50 and feel pretty confident that we're going to have a safe enclosure. So the basic physics say that insulation on the outside means that the wall is much more resilient from a moisture perspective. In addition to that, the perfect wall reduces or almost eliminates thermal bridging through framing members. It makes air barrier continuity a lot easier to achieve. It's kind of like you're wrapping a package as opposed to trying to make the air barrier continuous through geometric jogs and so on like that. And it works in any climate zone. So you could adjust the R value depending on how harsh the climate was, but the physics of the thing work in any climate zone. Okay, so we took that concept in 2004, before I was at the university, and constructed these four homes for the Wilder under a grant from the Wilder Foundation. The diagram on the left shows the layers. So the idea here is the perfect wall. We can see that the physics work, but it's kind of expensive. And so the idea was, is there a cheaper way to build the structure so that we can apply the slightly more expensive control layers and achieve the perfect wall, at basically zero net increase costs. So the diagram on the left shows the layers. This is a studless wall construction. So there are two layers of 1.125" thick oriented strand board. So the whole package is 2¼ inches thick, and they're cross laminated. They come in very large sheets, 8 foot by 24, and one of them is laid horizontally and one of them is laid vertically, and then they're glued and screwed together. So those four houses were constructed, and then in 2014, the DOE Building America program funded us to work with Habitat for Humanity and Urban Homeworks, and we proceeded to build several houses with them using the same technology, but a standardized plan. And in addition to that, there's a private developer that's been pursuing this technology. So I'm going to throw out the number 18. That's probably not exactly the right number. I'm not quite sure what it is, but more than 18 homes and counting have been constructed in this way. So then come 2019, and we were hired by Pacific Northwest National Lab to do in situ field testing for a study they were doing on wall upgrades, a techno-economic evaluation. And we have a test building up in Cloquet called the Cloquet Residential Research Facility. So we decided that we would make one of our test walls basically a single layer version of that whole house system. So we reduced the thickness of the oriented strand board because we didn't have to support the house anymore. But other than that, the control layers were essentially the same and used it in a retrofit application. So in the middle there, you can see the test bays. The base wall was an uninsulated 2x4 stud wall with lap siding. Below that is a plan of our building in Cloquet, showing each one of those individual boxes is a test bay. And then on the right is just to give you a sense, that's a station in one of the bays where the data from the walls comes and gets collected and then sent to a data logger in the basement. So in the middle here is a diagram of the wall section. So you can see kind of in the middle there, there's lap siding. So that layer and everything to the right-hand side of it are the base case walls. So you can see the stud frame, the gyp board, the board sheathing. And then to the left of the siding is our panel. So it's got the oriented strand board, substrate, the structure for the retrofit panel. It's got a membrane, it's got graphite enhanced EPS foam, and then a metal siding cladding. And then you can see the little colored shapes here represent our sensors. So the green triangle is a relative humidity, and the red triangle is temperature. And then to the right of that, the photograph shows one of these typical stations. This is at sensor position 4 as it's labeled in the diagram. So you can see there's little wires going to little dots. Those are brass nails that are embedded in the various layers of wood to measure moisture content. And then that little white package contains a thermocouple, temperature sensor, and a relative humidity sensor. So we laid out the premise of the perfect wall. How did our data reflect that? So what you're seeing here are three diagrams that show temperatures. So the black line is outdoor air temperature. The orange lines, there's three of them, one reporting from each of those three locations that are pointed out with the red arrows in the picture. And then there's a blue line that's just a straight line that shows the indoors is at 70 degrees Fahrenheit. So in the top, the base case, which is uninsulated, you can see that the sheathing temperature there kind of floats between the indoor air temperature and the outdoor air temperature. It's connected to both. Then in the cavity insulation case next to that, we've insulated the cavity and we've decoupled the sheathing there thermally from the inside of the building. So you see the temperature of the sheathing pretty closely matches the outdoor air temperature. Now with the overcoat approach, insulation's on the outside of the sheathing, we've decoupled the sheathing from the outdoors, and you can see that the temperature of the sheathing is tracking just under the indoor air temperature. So the temperature data seem to support the theory. Here we're looking at relative humidities instead of temperatures. The black line at the bottom is showing outdoor air temperature, and all the other lines are showing relative humidity. Now, there's a lot of lines on here, I realize. So there's 8 different walls and 2 orientations, there's a north and a south. So that's why there's so many lines, but I just want to point out a few of them. Those 2 blue lines at the top are one is north and one is south of the cavity insulation case. And you can see that relative humidities there are varying between 80 and 100% RH. Now, I forgot to mention, both of these data sets are the same periods of time. They're in February of 2021, so cold weather. The dark blue line underneath those light lines and kind of in with the green lines is the uninsulated case, the base case, the sheathing RH. And there the RH peaks around 80%, and then we can see it declining over time. Now the red and the purple lines below that are the overcoat examples. So you can see here, they're maintaining right around 50% RH for the duration in this cold weather, which tends to be when you might see some high relative humidities. So we can say that we would consider a very safe moisture regime as opposed to the blue lines. at 80 and 100%, which we raise our eyebrows and start to think that looks kind of risky. The other key aspect of the project is the deployment system that we identified and are proposing. Energy sprung is a concept that emerged in the Netherlands over the past decade and has since spread to other European countries. And it's starting to appear in the United States, particularly in the Northeast. The business model is really the first key of the system, but we're not going to talk too in depth about that in today's presentation. It involves aggregating demand by enlisting customers, fairly large numbers of customers, which incentivizes panel producers to invest in the technologies that make this possible. The process itself involves highly detailed measuring of the building. And typically they use a 3D laser scanner for that. And that's a technology that's fairly widely available around the country and in Minnesota. Excuse me. The laser scans then are used to produce 2D representations of panels that will precisely fit the building. They match door and window openings, penetrations, building geometry, etc. So then typically large format, large panels are produced in factories that use CNC machines, computer numeric controlled machines that are driven by the data that was gathered by the 3D laser scanner. An example of one of those panels from France is shown there on the left. And then on the right, you can see the idea, like here we have a building as it exists, and we simply come and overclad the entire building with these prefabricated panels very quickly. So windows, doors, and cladding are all installed at the factory, and then the panel arrives on the site ready to install by crane. New integrated mechanicals have to be added to meet the reduced thermal loads. You've super insulated the building. We need to ensure good indoor air quality because now they're much more airtight. And also this enables electrification. So let's talk about the system itself, the system that we've designed in this paper. So here's the overcoat panel. It's very similar to our whole house construction technique. There's an OSB structural panel to which a membrane is adhered that controls air, water, and water vapor. As I mentioned, we use peel and stick for this study. It could be a liquid applied membrane, could be other things. Rigid insulation is installed over that layer, followed by furring strips. Those furring strips are mechanically fastened back to the OSB with screws or bolts and T-nuts. And they tie the panel layers together, and then they also provide a fastening location for cladding, as well as providing for ventilation space behind the cladding. Geez, we're having all kinds of stuff going on around here. It's not helpful. The color code on the lower right appears in the subsequent drawings you can refer to as a sort of a key to the colors that we're using for these layers. So these are two panel-to-panel joint details. The first one is a section, and the second one is a plan. I'll mention briefly, in a number of our cases up in Cloquet, we wondered what would happen if we left the cladding on, the siding in the case of the Cloquet testing, simply because there may be lead, there may be asbestos, there may be reasons why you don't want to remove it. And in any case, it costs more money to demolish the cladding to install a retrofit. And in cases where we left it, we use what we call a squishy layer, is the technical term. And that layer is a compressible but drainable material that just serves to limit air movement behind the panel. All the joints strive to maintain the continuity of the control layers. So we're talking about the membrane and the insulation. And offsetting the layers as they progress from inside to outside helps us achieve this. The most challenging connection is the air, water, vapor control layer, that peel and stick membrane. So the sequence would go like this, and these drawings all kind of share this language of detail. So the lower panel we assume to be already fastened to the building, the lower panel in the section drawing on the left. The membrane gets pushed proud of the panel surface using a wedge or shape like that that's compressible, made of something like an open cell foam. So this pushes the non-sticky side of the membrane out and presents it to the sticky side of the membrane that's about to meet it. So on the upper panel that's about to be placed there, the non-sticky side of the membrane has been glued to the back of the insulation, and then the release paper that comes on the peel and stick is left in place right there. And right before the panel goes in, the technicians on site would remove that release paper and then compress these two together. So it's lap shingle style, but then it's also adhered so that it maintains good air barrier continuity. And then insulation layers are offset so that we don't get airflow between the insulation panels at the joints. We played around with this idea a little bit. We didn't explore it for all the details, but this is a detail where we looked at using what would happen. Could we use a vacuum panel, vacuum insulation panel, also called VIPs? The reason we would use that is because you can get about R20 out of a 1-inch thick VIP, so you can make a thinner overall package. The main challenge with VIPs is that they can't be punctured because then you lose the seal, air enters the thing, and then the R value drops to something fairly insignificant. So you have to absolutely protect them from fastener penetrations or any other kind of damage. So we developed this mounting block concept. The blocks would be made from some kind of low conductivity plastic or something like that. They, instead of piercing the VIP, they sort of trap the VIP against the panel, and then cladding would be fastened to that mounting block. So these are outside corner designs, and we've got a couple options here. And the reason for that is, we're speculating about the best way to do this, but we don't necessarily know what's going to end up working the best in the field. So here's two designs. One involves just simply mating the layers at the corner with the two panels that meet at that corner. And in the one on the right, there's a prefabricated corner block that actually that makes the connection between the two sidewall panels. Now, so far, I've showed you joints that are blind, meaning that the air barrier connection cannot be seen. We use that compressible wedge so that we know that that connection is going to be good. But it may be preferable to do that connection in the field so that you can verify that that layer is continuous. So this is an open joint concept. This is the only one of these we'll show, but you can do this with inside corners and all the other types. Here, the air barrier of one panel is connected to the air barrier of another panel. And when I say air barrier, I mean the membrane, which is actually controlling air, water, and vapor. So pardon my shorthand. But those are connected manually using a strip of membrane material. Then a prefabricated plug would be used to conceal the connection. So here are inside corner details. These are blind details, although you could also develop an open detail where that seal is made manually. So doors and windows are pre-installed in the panels. The panel comes out ready to go, ready to hang on the building. So flashing details for doors and windows are similar to standard new construction. But we just use, flashings with longer legs to make it out to the outboard edge of the flashing and the cladding. Since existing doors and windows are removed, we use jam extensions on the interior to conceal the rough opening and to come out and meet the plane of the new doors and windows. We anticipate that the foundation is going to be important. We need to insulate it, air seal it, waterproof it likely. At a minimum, we would recommend adding exterior foundation insulation down to the frost line, but it could also be taken all the way down to the footing. Foundation insulation and waterproofing that operation would be performed before the above grade work. And there's a lot of ways to do this. We have a project on excavationless foundation insulation, which is a potential candidate. The critical things are to connect the air barrier of the foundation, which would probably be the waterproof coating, to the air barrier of the overcoat panel, and to connect the foundation insulation to the overcoat insulation in about the same plane. So then we move on to a few roof details. So in some cases, you might have a half story, or other cases where you want to condition the attic. And in this case, you can use something like the overcoat panel on the roof at the roof plane. This technique has commonly been called a chainsaw retrofit because you remove the soffits. So the little scissors icon there on the left-hand drawing is showing that the existing soffit being removed. This enables you to wrap the air barrier over the transition from wall to roof, and the same with the thermal insulation. So you get a very simple geometry where it's easy to make things continuous. Then after those panels are installed, then new soffits and new substrate for the roof and roof finish material would be added on top of those assemblies. Here on the left, there's a sloped roof with attic floor insulation, and then on the right is a flat roof with no parapet. So just illustrating the concept that the air barrier in the ceiling needs to be connected to the air barrier on the panel, and the thermal control in the ceiling is connected to the thermal control in the wall as well. Here's a parapet on these are both flat roofs with parapets. On the left, we wrap the parapet. So this would be appropriate if your parapet is masonry or framed out of steel. And on the right-hand side, we take the thermal and air control through the parapet. So if you have a wood frame parapet, something that's fairly low thermal conductivity, it'd probably be accomplished with spray foam in practice to connect the air barrier and the thermal control through the parapet. And then finally, a way to hang these things. So this concept is derived from a French cleat, which is commonly used to hang cabinetry. And basically, there's a strip that is mounted to the structure of the building, and there's a corresponding strip mounted to the backside of the panel. And those strips have sort of sloped mating surfaces so that as you apply gravity loads, the sloped surfaces draw the panel in toward the building. And then you could use a small number of screws or other fasteners to finally secure the panel in place. Now I think Connor's going to come on and talk about good candidates. Thanks, Connor.
Yeah, absolutely. And thank you, Garrett. So as we were thinking about how to apply and scale Overcoat across Minnesota multifamily buildings, we first wanted to determine what makes a good candidate building and what makes a poor candidate building. So a good candidate building would be rectilinear in shape, have large flat surface areas, and would be 5 stories or less. Poor candidate buildings have integrated structural elements protruding from the facade or irregular shapes that would make it difficult to apply that flat overcladding system and get it close enough to the facade and create that squishy layer. We also noticed that many buildings would have required alterations. Some of these alterations would be a temporary removal, while others would be permanent. For the temporary removal, you see on the photo on the left, we've got a simple wooden porch that can be taken off of the building, the overcoat system applied, and then put back on. However, on the building on the right, likely that roof feature would need to be removed completely, and it would change the appearance of the building. Now, outside of major architectural changes, there are other features that need to be considered as well. So these would be things like sleeve air conditioners or drain pipes, electrical or gas services, or wall venting. All those things would need to be either removed and replaced or altered slightly. Now, once we had some of these prerequisites in place, we started to really funnel down the Minnesota multifamily building stock to those that would be amenable to retrofit. Now, we used a 2013 CARD-funded multifamily characterization study to help us. And so we started off with 440,000 units within the state of Minnesota. And then we brought those down to just the units that were going to be built before 1990, or about 300,000 units. Because we know after 1990, these buildings are going to have, some reasonable level of insulation already. Then we brought that down a little bit more to buildings less than 5 stories. And that's really because of some of the structural constraints with the overcoat system, as well as some of the fire testing requirements over 5 stories. Then lastly, we use imagery of the characterization study to really get down to what buildings could be retrofit. And that came out to about 40% of the total number of units in Minnesota, or 179,000 units. Somewhat surprisingly, the decade that these buildings were built in really didn't necessarily determine which buildings would be best for overcoat. All of them had a pretty high level of amenability. Now, it's also important to consider HVAC impacts. So I'm going to start on the upper left here and talk a little bit about these remaining units and their heating systems. So it's a pretty even split between hydronic boilers that are non-condensing, centralized, providing heating, and then electric baseboard. Now, the remaining heating systems are a little bit of hydronic centralized condensing boilers, some furnaces, and then just a little bit of steam heat still. When it comes to cooling systems, we saw 66% of these units having sleeve ACs and 28% with window ACs. Both of these systems really degrade the thermal performance of the envelope. So these would need to be replaced, likely with split systems or split heat pumps. When we look at the domestic hot water systems, the vast majority are centralized systems that are non-condensing, so 75%. The remaining 25% is really a mix between electric or gas individual units, some centralized gas condensing, or systems that are interconnected with the heating system. Now, it's important to think about the exhaust of flue gases with the non-condensing systems, as we're going to be sealing these buildings up pretty significantly. Lastly, what bills are tenants typically paying within these buildings? 90% of tenants are paying only their electrical bills. The remaining are the landlords are then paying the gas bills and the heating bills for them. So if these systems were to be changed out from these centralized gas heating systems over to heat pumps, considerations would have to be made around the total cost of housing, which is going to be rent plus utilities. And this goes for not just overcoat and overcladding and switching out systems, but also really moving these systems or transitioning them over to heat pumps. Now I'm going to talk a little bit about building characteristics. So here you see 4 prototypical buildings that were taken out of the Minnesota multifamily characterization study. And these were used for both our cost and our energy analysis, and they provide a good representation of size of building, type of envelope, and age of construction. So here you see some of the parametrics that we had simulated. And in this table, we've got the metric on the left, our 4 prototypical buildings and those starting points in the middle, and then on the right, the upgrades that we included. So for our 4 buildings, they ranged in size from 5,000 square feet up to 56,000 square feet, or 58,000 square feet. They were between 2 and 3 stories. And then they had all the way down to 5 units up to 123 units. So a pretty good range there. When it comes to the exterior wall construction, We started with standard framing elements or brick cavity walls with no insulation, and then also looked at what happens when those buildings did have a little bit of insulation, typically that insulation within the framing. And then for the upgrade, we looked at two R-value components for Overcoat, R20 and R30. Ultimately, we think that the R30 levels can be reached cost effectively with the level of thickness of insulation applied. For the roof constructions, we started off with typical batt insulation or some loose fill depending on construction type again. And we're pretty confident that these buildings, as part of the overcoat process, could get that insulation up to about R60 for the roof. Based on the age of construction of these buildings, we assume single pane windows, and with overcladding, we would be proposing to put in triple pane windows. We looked at the sensitivity with infiltration, as this was one of the largest drivers for energy use, between 4 and 6 air changes per hour within the baseline condition. And then we believe we can get down to about 1 air change per hour at 50 pascals with that overcoat system. When it comes to the HVAC side of things, 2 buildings had electric resistance heat and with through-wall air conditioners, and then 2 buildings were hot water boilers with through-wall air conditioners. When we did the analysis and cost exercise, we looked at both keeping these existing systems in place as well as retrofitting all conditions with mini split cold climate heat pumps. Lastly, for ventilation, starting point was bath fan only exhaust driven ventilation. And because these buildings will be so tightly air sealed, we included for all simulations a 75 CFM in-unit ERV providing balanced ventilation. Now we'll get into a little bit of the modeled results and savings. So on the left, you can see the EUI, or energy use intensity, for our 4 buildings within the pre-retrofit condition, and then stepping through overcoat plus ventilation, and then adding in that heat pump conversion. Big takeaway is that all buildings had greater than a 45% reduction in energy use with just that overcoat system and that ERV. So that's pretty astonishing. If you included those heat pumps in lieu of either electric resistance or the gas heat, that would improve that EUI savings between 75 to 60%. When you translate that savings into utility cost savings for tenants, the most impactful is really for the electrically heated buildings, and that's essentially driven by the higher cost to heat with electric resistance as opposed to gas. Last thing we want to mention here for now is that each of these buildings will have the potential with the heat pumps to be net zero ready with EUIs less than 30, allowing for rooftop solar offsets. So here we're summarizing both the savings and costs for the overcoat panel system, and then the additional mechanical costs. And these mechanical costs also include, here in this table, the inclusion of the heat pump retrofit. So as we look across each of the 4 buildings, sometimes the overcoat panel system costs a little bit more than the mechanical upgrade costs, or vice versa. And that's really dependent on the aspect ratio of the building and number of units. So enclosure area to floor area will drive that consideration. When we start to include the annual energy cost savings with the total upfront incremental costs, we see a pretty stark range in simple paybacks. So the 2 buildings with electric resistance heat had simple paybacks of around 22 to 26 years. And that's based on $21 per square foot for the overcoat enclosure, and then $25 per square foot of floor space for those mechanical system costs. Using those same costs, however, with gas heat, we're seeing simple paybacks over 100 years. Now, if we're able to, even if we removed the cost of those mini split heat pumps, those simple paybacks would be about 50 years. Now, all of this cost data was really taken at the start of this year, probably towards the height of some of the inflation of construction costs. And really, we've seen gas costs start to rise as well from those at the start of this year. So if gas costs continue to rise and the estimated cost of the overcoat system starts to go down, these can be more viable for gas heated buildings. A few points for takeaway here is that the Overcoat Panel System offers a building science-based solution for overcladding existing buildings, and that really provides radical reductions in building energy use. Due to the decreased thermal loads, increased air tightness, and mechanical systems must be upgraded at the same time. And this is especially true for HVAC systems like through-wall air conditioners or window units, which degrade that thermal envelope. The costs for the system are currently being estimated as very high, likely precluding retrofits right now for buildings heated with natural gas. And innovative building models are going to be needed to stimulate demand and supply. So really trying to aggregate that demand side of things while also working with builders to start to tool up to be able to produce these panel systems. And lastly, pilot projects are going to be needed to start to refine that panel detail.
Great. Thanks for that great presentation. If you have not already done so, please type any additional questions you have into the Q&A panel and send them to us. Laura, do you have questions for Garrett, Connor, or Liz at this point?
All right. Yes, thank you for the great presentation. Can you talk a little bit about when do you think a system like this would be ready for prime time or wide adoption? Your thoughts on that?
We're ready to go. We just need somebody to build a plant. I mean the fundamental physics are worked out, and the energy picture based on our previous experience, we're pretty confident about the kind of energy performance and the air tightness performance of the system. So I think the fundamentals are worked out. I think it's kind of up to others who probably have brains that work differently than mine to work on this business model problem so that we can. It's sort of a chicken and egg problem. You have demand, but you have no industry. You can create an industry, but if you don't have demand, that's not going to work. So we need some kind of innovation in that space to kick off what is a pretty heavy lift. I mean, we've picked the low-hanging fruit and energy savings to a significant degree, and kind of the next step that we're seeing is overcladding buildings. So doing that cost effectively is I think what we're all after.
I have a question. Do you have any calculations around carbon reduction?
We do. I believe those are were not included in our draft final report for this. It's something that we could follow up on with you on the direct carbon reductions. We do see a difference, of course, between looking at the electric resistance heat to the gas heated buildings as well. But ultimately, by adding the overcoat system and those drastic energy reductions, we are seeing a very positive outcome on the carbon footprint side.
All right, another question. Can the overcoat panel be prefabbed with mini splits in mind to replace window or sleeve units?
Yeah, I think in the case of a sleeve unit, you would sort of automatically be canceling that device and the overcoat panel would roll right over that. Yeah, where cooling is desired, I think you have to move to a different cooling solution than window units or sleeve units. So the windows would be in the same locations and the same size. You just wouldn't put an air conditioner in them, but the sleeve units would have the panel basically canceling that opening where the sleeve unit had previously been.
Yeah, I'd say we suspect that you would, even with the highly insulated envelope, you would still want air conditioning across the Minnesota climate. So
Yeah.
it is a change that would have to happen.
All right. Possibly the most cost-effective time to implement this retrofit is when the building needs to be re-sided and our space heating or cooling equipment needs to be replaced. Did you estimate what the cost would be for that work and how the simple payback would decrease if you only included the net cost of the overcoat?
That's a really interesting question. The first thing that comes to mind is we we submitted a card grant for a white paper, and at some point we had to just, despite our curiosity, just have to say no, that we'll save that for a different day. I think it's a really interesting question. That would be good to dig deeper and understand. And then how do you get in there at the point when the building owner needs to do something like this? How do you show up at the right moment in time with the right technology so that you get your solution installed as opposed to, something that's probably lesser? Do you have anything to add to that, Connor?
No, I do agree that finding those retrofit cycles is going to be important. I think with affordable housing, that's a little bit easier to pinpoint sometimes as those start to get refinanced and looked at after about 15 years. Other multifamily buildings might be a little bit more challenging, though, to pinpoint those retrofit cycles. But I think you're absolutely right. These updates need to be aligned as these projects start to get recapitalized and thought about those refreshes. So.
Great. Okay. Well, if we don't have any more questions, so audience members, if you have questions, please put them in the Q&A. Maybe you could just talk a little bit about kind of summarize your key takeaways for utility program administrators at this time.
Yeah, hi, Liz here. And Connor, and there was already a question about decarbonization, but for us that seems like a huge benefit to this. Either or both for retrofitting all electric buildings to create space in the grid as it increasingly decarbonizes, and then of course transferring from natural gas or other fossil sources to the electrical grid, while keeping in mind that broad electrification will increase the demand on the existing grid. So anything that can be done to decrease the demand without expanding the grid infrastructure will result in avoided costs. And then there's also some, I would say, implications for resilience. Buildings that are better insulated or will be able to withstand any kind of disruptions more easily, might reduce the demand on grid during peak times and of course on an annual basis as well. So
yeah, I just add as well, like just the significant energy savings to be considered. We're seeing upwards of a 75% energy reduction with overcladding and mechanical upgrades, and as Liz mentioned, some of those peak load reductions too. So we're switching over to electrification. We can cut back on those especially the winter peak demands. And I think The overcladding system goes well beyond conventional weatherization retrofits as well, where we can start to see really utility costs decreasing for tenants as well as you switch from gas heat over to electric heat. It's another takeaway.
Great. Thank you. All right, Mary Sue, I'll turn it back over to you.
Great. Thanks again for that great presentation, and to Laura for facilitating the Q&A. If you have any follow-up questions about this card project, feel free to contact one of us. The recording of this webinar and slide set will be available on the department's website in a few weeks, and the final report in a couple of months. When available, you can link to either of these from the quick links on our Applied Research and Development webpage, as indicated on this slide. The department's R&D webpage has additional resources and information related to the CARD program and to CARD research projects, which you can check out by going to the link at the bottom of this slide. Thanks for participating today. We really appreciate your interest in CARD projects, and I just want to take a minute to mention an upcoming webinar in December, on December 7th of 2022. Ecometric will discuss the results of research they conducted into the motivations and barriers that drive the decisions of individual HVAC installers working in small to medium commercial buildings. To keep abreast of upcoming CARD webinars as they are scheduled and other news related to the Minnesota Conservation Improvement Program, sign up for SIP updates through our email list. You can use the link on this slide to do that. In the meantime, contact me directly if you have questions or suggestions for the CARD program or CARD webinars. And as a final reminder, there will be a short evaluation that launches after this webinar. Please take a few minutes to fill it out and let us know how we did today. Thanks, and have a great rest of your afternoon.